Inside a high-volume fulfillment center, the single largest operational expense is labor. Managing that expense requires matching the exact number of people on the floor to the exact number of packages arriving at the dock. But the incoming volume arrives as a chaotic, unpredictable force. It surges in nonlinear waves throughout the day, dictated by when customers click buy and when delivery trucks reach the yard. Human labor cannot be shaped to perfectly fit those waves. It has to be procured in rigid, fixed blocks, usually 8 to 10-hour shifts governed by labor laws, rest days, and human fatigue. If a site manager attempts to solve this mismatch by calculating headcount against a daily average volume, they will fail. They will be severely understaffed during the afternoon rush, breaching service level agreements, and overstaffed at midnight, burning through the budget. Bridging the gap between liquid demand and rigid capacity requires sales and operations planning. The process relies on the multi-step algorithmic derivation of headcount and shift optimization to calculate exactly what is needed hour by hour. S&OP serves as the physical translation layer, converting nonlinear demand into a cost-efficient, rigid structure of human capacity. To build that capacity structure, the calculation has to start at the lowest level of granularity, role-specific throughput inside the warehouse. This table shows the exact headcount required for every specific operational role, broken down by the hour for a Monday shift. Notice how productivity is entirely dependent on the task profile. Look at the water spider role, the worker responsible for securely wrapping packages. A single water spider can process 2,000 small, conveyable items in 1 hour. But if the volume shifts to large, heavy, non-conveyable items, that same person can only process 45 packages per hour. Because volume and task profiles fluctuate throughout the day, the daily headcount requirement is calculated by dividing incoming volume curves by these specific productivity rates to find the absolute maximum hourly peak. Here, the data points directly to 14 hours as the critical constraint for Monday. The site must have 33 active workers on the floor at that exact hour to clear the volume. Missing that target by even a few people during the peak hour guarantees a backlog, which then cascades into the subsequent shifts and slows down the entire network. But this peak requirement is not static. Looking at Saturday's data, the total incoming volume tapers off, and the required peak drops down to 24 people. Daily operational capacity has to be reverse-engineered directly from these isolated hourly peak constraints, never the daily average. Knowing the required peak is only half the equation. The site must now procure that labor by scheduling weekly shifts. This table outlines the available shift catalog. There are full-time contracts working 6 days, 5 days, or 4 days a week, each carrying a different weekly cost and different required rest days. The optimization problem is straightforward. Map these shift types against a week where the daily demand fluctuates from 34 workers needed on Tuesday down to 24 on Saturday. Scenario A attempts to solve this by hiring exclusively full-time employees on 6-day schedules. This covers the Tuesday peak, but it creates expensive overstaffing on Saturday. The site ends up paying for idle capacity. Scenario B relies on 5-day workers and fills gaps with daily contractors, known as diaristas. This drives the total cost up drastically due to premiums. The lowest cost is Scenario C, combining different full-time schedules to exactly match baseline demand. The core workforce is set at 24 employees working 6 days a week, plus 9 employees working 5 days a week. To handle the specific micro-peaks on Tuesday and Thursday, the algorithm deploys exactly 2 diaristas. The site covers 100% of the volume without carrying any dead weight into the weekend. Labor optimization functions like a geometry problem, mixing rigid contractual shapes to perfectly fill an uneven weekly container at the absolute lowest cost. That solves the problem for a single week. To run the facility properly, planning extends to a 12-week strategic horizon. Over 12 weeks, market volatility generates volume swings of up to 10%. Constantly hiring and firing permanent staff to match these swings creates friction, damages team engagement, and incurs heavy severance costs. The structural response to this volatility is the base plus flex methodology. Instead of chasing the total forecast, the full-time permanent headcount is locked to the 60th percentile of the projected demand. Looking at the 12-week forecast table, the raw headcount requirement bounces erratically, dropping to 29 people one week and spiking to 36 a few weeks later. By locking the full-time base level near the middle of that variance, the permanent staffing requirement is smoothed out. This stable baseline safely covers operations without exposing the site to overstaffing risk. For weeks where volume pushes above the base, like weeks 31 and 32, the site triggers the flex layer, deploying daily contractors to absorb excess demand. Each week, operations teams compare the actual volume to the forecast. If there is a shift of more than 5%, they adjust the flex layer of contractors, leaving the permanent base untouched. Strategic S&OP deliberately isolates market volatility into a flexible buffer to strictly protect the stability of the core permanent workforce. The mathematical model is locked in, but a theoretical plan is useless without daily, floor-level tracking to ensure reality matches the spreadsheet. Execution is tracked using the Staffing Efficiency Rate, or SER. It compares the actual headcount working on the floor to the optimized plan calculated the week before. A healthy site maintains an SER between 95 and 105%. If absenteeism pushes the rate below 90% for 2 consecutive days, an emergency trigger is pulled to activate extra contractors and stop a backlog before it starts. That headcount check is paired with an output metric, packages per associate hour, verifying that the workers on the warehouse floor are actually hitting the productivity rates required by the model. Workforce optimization is an active, closed-loop system. Floor realities constantly stream upward to recalibrate strategic algorithms, ensuring the math always translates into motion.